3D stock is an empirical model founded on a simple question. Can we account for the energy performance of the building stock? More specifically, can we link the geometry of buildings to other data that might influence the energy performance of the buildings? We use map data, addresses, and a range of other data sets to draw this together in a geospatial model of buildings to try and answer this. And we've done this for Greater London, Sheffield, and we'd like to do a lot more towns and cities because we think that this can help to tackle the energy performance of buildings, and that is something that we need to improve if we're going to reduce greenhouse gases to net zero by 2050. There have been improvements over recent decades, but this rate of improvement is nowhere near as rapid as it needs to be. And in the chart on the right, some people have recently classified it as a flatlining sector. The model we will show today focuses on Greater London, but we can build these models for anywhere. And we have ambitions to extend the model to the whole of Great Britain. Whilst buildings generally account for around a third of the UK emissions, buildings in big cities like London have an even greater share of total emissions, closer to 65 to 75%. I'm Steve, and I'm going to give a simple overview of how the model works and touch on what the model can be used for. And then Daniel is going to take you through a deeper dive into the analysis of the model. So this work is funded by CREDS, which stands for the Centre for Research into Energy Demand Solutions. And CREDS works with researchers, businesses, and policymakers to support the transition to a secure and affordable low-carbon energy system. In addition, the Greater London Authority asked us to develop a model of London, and this work is part of that model. At the Building Stock Lab, we talk to a lot of local authorities at the moment, and nearly all of them ask us, how can we achieve the net zero emissions targets by 2050? So firstly, our model confirms that you clearly can't achieve this by just building new energy efficient buildings. Retrofitting existing buildings is essential. And whilst our model can't solve this physically, it can identify those parts most in need of energy improvements or those areas that show the greatest potential for improvements. And when we break this down into what I think of as questions that shovel-ready projects might ask, then some of the queries we run are actually very simple, but pretty essential questions to ask. Questions like, how much roof insulation is required if the EPC recommendations are followed for all homes? Or what is the average exposed wall area per house type? Or how many buildings have flats above shops? You need to be able to measure these things if you want to improve them. The way we do this is to use the most granular data we can access, and this means the model is able to simulate not just buildings, but the different activities within the buildings, as well as some of the materials used to construct the buildings. So to help illustrate this, I'm going to whiz through a thin wedge of the building stock that we can all relate to, mid-terraces. First point, there are quite a lot of these in London, but not all of them are houses. And the second point is that 3D stock is not an archetypal model. So archetypal models would use a model of, let's say, one typical mid-terrace building in this case, and then it would multiply it up by the total number in the region. In this model, every single one of the 700,000 mid-terrace houses is different. We deal with both domestic and non-domestic in the same model, which means we can pick out mid-terraces that are not used as houses but are used as offices, or we can even pick out a combination of shops and offices. And we can unpick this detail and we can then account for another 19,000 mid-terraces which have non-domestic occupants. Then there are those which have both non-domestic and domestic sharing the same building. And this adds another 34,000 buildings. So by now you can hopefully see that buildings and their occupiers don't always have a one-to-one relationship. This annoying fact is really important to grasp. And it works both ways. So some like this one can have many premises or dwellings to one building, whilst in other cases, a single premise premises can have many buildings like this one. So assuming a one-to-one relationship is a dangerous trap to fall into. And 3D stock maintains this complex relationship. Finally, there are those with multiple domestic addresses, namely those that have been converted to flats like this example. And there are quite a lot of these, 117,000 of them. Add them to what we already have and it totals around 870,000 mid-terrace buildings in Greater London. So whilst I've kept this simple, I'm hoping that you can see how that we can dissect different parts of the stock in great detail if we want to. Obviously, the model includes a lot more than just mid-terraces, but we do exclude a few buildings, and these would include things like premises in railway arches and kiosks. But we include pretty much everything else, and some of the buildings can be enormous, as big as the John Lewis Distribution Centre, known as Magna Park, which has got 7 hectares of floor space. But obviously others are tiny, like little coffee shops. So for us, a building needs to be a permanent roofed construction with walls and a footprint that exceeds 8 square meters. To pull these buildings into the model, we use a number of key data sets. So we make good use of Ordnance Survey data, and this gives us georeferenced UPRNs for every address. Business rates can then be matched to these addresses to give us useful insights into the non-domestic activities at each address. Large-scale map polygons, along with LiDAR data, gives us the 3D buildings. And then land registry gives us property boundaries. And from here, we can introduce energy performance certificates and display energy certificates. And in fact, we can introduce any other data with an address or a location. So just like the mid-terrace buildings that I showed, this means that we can then show the degree of mixing that occurs in each building, ranging from single occupant non-domestic buildings, which obviously have no mixing, through to single occupant, single household houses, shown in dark blue here. And then in between, there's a range of mixtures. And this means that we can look at cities through quite a different lens. And that can highlight just how extensive these mixed buildings can be. So when we chart this to compare the spectrum of mixing between local authorities, it becomes clear that some, like Westminster, have huge volumes of the stock that are mixed. And this obviously has implications as to how retrofits can be carried out. Floor space is a key component of the model, since it normally has a strong influence on total energy use. And the VOA store this in detail for most non-domestic premises because most business rates are paid based upon floor space. But this isn't the case for domestic spaces, which means that we've got a data shortfall here. And so to get around this, we've developed a way of estimating this inspired by voxel-based approaches to medical imaging. So a voxel here being a pixel with volume rather than the part of London where MI6 are based. The method is not perfect, but when we compare 300,000 houses to a known measure of domestic floor space like EPCs, we get a reasonably good correlation, as you can see in this hex bin plot of houses in the model. All of this wouldn't be possible if we couldn't join different data sets together. And sadly, most of these data sets were not designed to be fitted together. And on top of that, they're often messy or have inaccurate addresses, or they're just really poorly formatted. So to bring this data into the model, it has to be matched to a gazetteer. So in our case, the OSAB data set. So this is not a very exciting part of the model to describe, but you can see in this fictional case on the screen that you have to find similar matches and then sift for the best match. And you often have to accept an imperfect match as being the best match that you can find. But the crux of the problem, however, is obviously to reduce energy use in buildings, and real energy data is invaluable here. So under strict confidentiality agreements, we're fortunate enough to have gas and electricity meter for London from BEIS. And I say fortunate, but this is not without its problems, because obviously the topology of meters to buildings is usually simple, but can actually become very complex, as you can see in some of these examples that are coming up on the screen now. And if you didn't link the data to the buildings, you might not be aware that these complexities existed. Secondly, whilst electricity meters have a very good classification system, the classification of gas meters into non-domestic or domestic is done by consumption threshold. 73,200 kilowatt hours per annum is the threshold. So this means that some small shops, estate agents and restaurants can be classified as domestic, while some blocks of flats that bulk purchase their gas can be classified as non-domestic. So BEIS acknowledge this issue, but our model could obviously help to resolve some of it. And just as a kind of COVID-19 related aside to this, I would guess that there are quite a few shops, estate agents and such like, that were not far above this gas threshold on a normal year, but may now drop below it for 2020. Once we have unpicked addresses and calculated floor space and assigned energy meters, then we can use Floorspace to help us to measure energy use intensity. So this is where we use the floor space in a building to normalize the energy used to give us a value in kilowatt hours per square meter per year. And this helps us to compare buildings of different sizes, but based on similar terms. We need to also know about construction materials and age, and so here we've used the classifications from Geomni for all the buildings. And this means that we can select all tall blocks of flats above 18 meters tall, which you can see highlighted in orange on the map here for some of the inner London boroughs. And you can then look at the exposed wall areas that might require insulating. So we can also look at the age of them and the construction materials, or we can break them down into very tall and medium height buildings. And at the same time, we can make aggregations of the data to show which local authorities have the greatest number of these and what the exposed wall area totals are, or both the total and the average numbers of flats that you would be dealing with if you were to tackle the retrofit of these big blocks. Obviously, not every house or flat has an energy performance certificate, but we wanted to work out what London might look like if they did. So we devised a method to estimate what we called a virtual EPC by looking for similar buildings close by with the same age, materials, and other characteristics. And by using these to produce an aggregate EPC or a virtual EPC. So this allowed us to fill in the gaps in the model and estimate the energy performance of almost all buildings in London. So you can see this best in the next sequence of maps. And this first one shows the mix of the stock, just like the one that I showed in the earlier slides. And here you can see Edgware Road running diagonally across North London with Brent Cross and Wembley Stadium picked out. The next shot shows you the buildings lit up by their energy performance certificates. But there are gaps and buildings are missing due to the lack of EPCs being everywhere. So this, the virtual EPCs is going to become really apparent when I go to the next shot, which is going to fill in those gaps. So if you pay close attention, then I'm going to click now, and you should see the missing buildings filled in with the virtual EPCs. Okay, so I'm going to finish my part with some examples of how the model can be used to identify areas where low carbon technology has the greatest potential. So the first tries to take us away from gas boilers and into heat pumps, specifically using ground source boreholes for NHS hospitals. So to do this, we estimated the theoretical heat pump demands based upon the hospital's current gas consumption, and then calculated whether there was the space to drill enough boreholes on the site to match this demand, following basic drilling requirements. So the aim was to find out if this was a viable low carbon heat solution for any hospitals. So not surprisingly, a lot of inner urban hospitals could not achieve the demand due to having very large heat demands balanced against very little available land. Others, like West Middlesex, shown here on the map, were just able to achieve the simulated demand. And if we look at the tabular data, we can see that a handful showed the potential to actually exceed this. So we're currently looking at applying similar code to work for domestic properties in the model. For the second example, I'm going to show you our solar potential model. So on the screen now is not a black and white aerial photo, but the 3D model showing solar potential. So light grey shows a high potential, and the grid cells are 0.5 metre in size. This is part of the Lee Valley, with the North Circular running across the top and Tottenham Football Stadium bottom centre. If I zoom in, then you can see the level of detail, and the 0.5 metre grid cells should be apparent in this close-up of the model. The colours show the solar potential in kilowatt hours per square metre per year if solar panels were fitted. So unlike a lot of other solar models, ours calculates for the effects of overshadowing by trees and other buildings. And there is an example in the bottom right here where there's a factory, and if you can see my mouse, you should be able to see a tree that has actually overshadowed the roof of the factory and affected the solar potential scores. So we can use this to identify rooftops or even land areas that show good solar potential. And we can combine this data with a host of other variables, including EPCs and energy demand. But for this example, I'm going to keep it really simple. We can split out the potential that the different building activity combinations offer. So firstly, we can pick out just warehouses, factories, and big retail sheds, which are shown here. So again, the colours show the roof space that meets a minimum threshold, with orange showing good potential, whilst dark red shows excellent potential for the latitude. Alternatively, we can pick out health and education, which lights up the schools, the small health centres, and North Middlesex Hospital, which is up in the top left. Or we can pick out just purpose-built flats, or we can pick out just houses with a single household, although this one's quite faint to see. So if we go back to just showing it all, then I'll just say two more things here, which is firstly, we've done this for the whole of Greater London. And secondly, there are some useful byproducts from this data, namely roof slope and aspect. So we can do things like picking out flat roofs, for example. Like all our data, you can engage with this at whatever level interests you. So as an individual, you might want to know the potential on your house, whilst as a local authority, you might want to know how much electricity could be generated on all your school buildings. The Mayor of London has set a 2 gigawatt target for the year 2050. And to illustrate this, I've compared Enfield and Haringey. And in these tables on the screen, the right-hand column shows the percentage that might be contributed to this 2 gigawatt target. So this shows that some local authorities like Enfield have an interesting conundrum. Houses show the greatest potential, but that would involve solar panels on tens of thousands of houses. Alternatively, they have a lot of warehouses, meaning that I think for 825 warehouses, factories, and big retail sheds, they could achieve nearly 4.5% of the Mayor's 2 gigawatt target for the whole of London. Obviously, this assumes that those buildings have good quality roofs that would support the weight of the solar panels. So our team has also worked hard on developing a user-friendly web-based interface to the model. And so you can actually try out a simplified version of the solar data that I just showed on the GLA website. And the same is true for the building stock model. So these are just screen grabs to show you how the model can be combined with a whole host of other variables like fuel poverty, air quality, and opportunity areas, to name just a few. And we'll put some URLs at the end of this presentation if you want to follow those links. Okay, so I've tried to give an overview of how it's possible to store data on all buildings and interrogate specific sectors like just mid-terrace houses or just tall buildings. And there are many more applications than I've had time to show here. So we've got modules that look at the viability of district heating and also look at the use of waste heat. And we've even explored the inefficiency of tall buildings, to name just a few other projects that have gone on. Obviously, you can get more complex than this if you want to, and you can slice and dice the data into pretty much whatever combinations you require. And so we think that this could help to inform policy decisions and to measure policy outcomes for the considerable investments in retrofit that lie ahead. Right, I'm going to stop there and I'm going to pass over to Daniel, who's going to take you on a deeper dive into our retrofit work in the domestic sector.
Hopefully you now have a good idea of what 3D stock is. So now we'd like to go through some more of the analyses that we've been using this model for. So at the simplest level, it's a highly detailed model of the building stock that allows us to examine the built environment across large urban areas. So if you're interested in MEES, for example, we could look at the distribution of EPC grades at the borough level, which is what I've shown at the top right. And here you can see that some boroughs have a larger proportion of their stock that will be affected by MEES or by changes to the requirements than others. And alternatively, if we were interested in building performance, we could analyze the energy data in conjunction with buildings data within 3D stock. So the bottom right shows some gas and electricity intensity cumulative distribution curves that we've produced for the domestic building stock. However, because there's no built-in aggregation in the model, we can also pick out individual buildings. So we can see, for instance, that this property is a gas-heated mid-terrace house with an EPC grade of E, and then compare its gas and electricity use against benchmarks for similar buildings. To date, we've used 3D stock in a number of areas, and so what we'll do now is to go through a few of these. In particular, we'll touch on the first three fairly lightly, and then I'll spend a bit more time focusing on some ongoing work in the fourth point there. So we've done a fair bit of work processing the electricity and gas meter data. As Steve touched on, this isn't a straightforward process, partly because of the need to address match these meters independently to the properties, but also because of the need to verify that buildings are indeed gas heated or electrically heated. And we do that through the matched EPCs. These are domestic energy intensity benchmarks that we produced on the left for gas intensity and on the right for electricity intensity. And these are specifically for gas heated dwellings. You can see on the left-hand side, in particular for gas, the influence of built form as gas intensity drops from bungalows and detached houses towards more compact forms of mid-terrace houses and flats. Now, we hope that these, subject to approval, that these benchmarks will be made available through the CIBSE benchmarking website. But we're also working on assessing how domestic energy use varies under different measures. So this is the domestic energy plotted in using different approaches, but for the same samples. The top shows energy use per dwelling, and you can clearly see the influence of floor area. And then the bottom uses the heated number of rooms in the EPC data to calculate the average energy consumption per heated room. Another thing that we've done is to look at how energy consumption varies with other building characteristics, including the EPC grades. So in particular, what we're interested in, this is some results that we've produced for Bays, but will hopefully be part of a paper soon. We've been interested in looking at whether or not gas and electricity use rise as you go from A to G grade houses. This is the results for gas heated houses as a whole within London, but the trend that you can see broadly holds true for other houses as well. So you can see gas intensity rises from A grades to kind of EF grade and then drops slightly to G grade houses, and electricity in contrast is relatively flat. We've also done a lot of work using the detailed geographic and physical data within 3D stock to explore how urban form and density can be quantified and visualized in more detailed ways than the simple dwellings per hectare type measures that are most common. So here are the dwellings per hectare for the 33 local authorities in London. To do this, we've been integrating 3D stock with a tool called Spacemate, which was developed by Berghaus-Upont and Hout in the early 2000s. And this is essentially a way of representing urban form and density at the individual building scale rather than at large aggregate levels. I won't go into this in huge detail, but essentially the y-axis is the floor area ratio, which is the total floor area of a building divided by its area of land. And the x-axis is the ground coverage, so the ground floor area divided by the area of land. And so what this means is that for each property, each building within London, we can calculate these values and then represent the whole of London on one of these plots. So this is essentially the distribution of all domestic houses in London, calculated from 3D stock. Now, because Spacemate essentially represents the relationship between a building and the urban space, you can see trends both in terms of the building characteristics across these plots, as well as the energy consumption. So this is the distribution of built form. And broadly speaking, what you can see is in green is the low density areas of detached and semi-detached housing. In orange, you can see terraced housing, and the large area of red is flats. So essentially, these are on the whole located in much more dense areas, but you can also see building height, which are the radial lines coming out. These are the relationships with energy use. So we've effectively plotted the graphs that I showed originally, the samples of gas heated homes onto Spacemate like this. And you can see how gas use intensity on the left and electricity use intensity vary across the Spacemate's plot in the same way. Just to note, I've removed some of this area here because the sample sizes are fairly small and we need to keep anonymity. We've also done a fair bit of work processing the EPC data in order to get a better understanding of the current characteristics of the stock. So this is an example of the kind of data that's available within the EPC bulk release. And we process this to understand what the buildings are now, but also to feed into a better understanding of where retrofits might be appropriate. So here you can see on the left is the distribution of the level of loft insulation in houses within London. And on the right is in the counts, you can see the proportion of houses with different wall types, as well as different levels of wall insulation. As well as feeding directly from here into getting understanding of the potential for retrofits, i.e. to know, for instance, what proportion of houses have solid walls without insulation. We're also interested in understanding the proportion of these houses that are recommended for improvements as part of the EPCs. We've also done a fair bit of work looking at what proportion of houses are recommended for envelope improvements based on their current characteristics. So for instance, here you can see in the second group of results how the proportion of buildings, houses in different construction bands are recommended for glazing improvement in red, or roof improvement or wall improvement in blue and green respectively. And these trends we've projected onto the stock as a whole, and you can see here our estimates for the proportion of houses across London that might be recommended for roof improvements, wall improvements, and glazing improvements according to the data that's available from the EPCs. So finally, talking about a bit of work that brings some of this together and wraps back to the Pathways to 2050 slide that Steve showed early on. Here we're using the building information from the EPCs in conjunction with meter energy data, as well as the geographic and form data in 3D stock, and using this all together to examine the impact of different policy drivers on domestic retrofits for London as a whole. So talking through the methodology, if we consider an example building, and I'll show data that doesn't belong to this specific building, this is a snapshot of some of the data available in 3D stock at an individual building level. So we might know that this is a mid-terrace property. We'll have building form information, including the areas of the building envelope. We also know about the construction, so here uninsulated solid brick walls. And finally, we know a bit about the internal systems as well as the annual energy consumption. And with all this data, we can identify the opportunities for improving the building. So having an uninsulated solid brick walls, this building might be suitable for solid wall insulation, of course. And using then the area of external walls, we can estimate the cost of making this improvement. And using the current energy consumption as well as the current building characteristics, we can estimate the impact on the home of such a measure being implemented. We can then carry out the same analyses for any other building. And crucially, unlike archetype-based models that might represent all of these with the same mid-terrace gas-heated house, we're able to consider the fact that each of these buildings has ever so slightly different form, existing materials, or performance. Now, of course, what this means is that although the example was just looking at applying solid wall insulation to mid-terrace houses, the order that the 4 houses are retrofitted in will impact on things like how quickly capital is needed or how quickly emissions are reduced for the sample as a whole. Or alternatively, the order that the retrofits should be rolled out will differ if the underlying drivers were, for instance, to make the biggest impact first or deal with the lowest hanging fruit first. So what we're doing at the moment is essentially to run that sort of analysis for all of 3D stock and considering not just solid wall insulation, but a number of different improvement measures. So we've written a module for 3D stock that calculates the impact and cost of retrofits for each individual property in the way I described previously, and then optimizes the order that houses should be improved for different user-defined scenarios. We've put together a simple tool that currently works in Excel, but we're hoping to give it a nicer interface that allows data from 3D stock to be processed, so different retrofit scenarios can be explored and compared fairly quickly. This is an image of the tool, and essentially each row represents a single retrofit pathway scenario, showing the way that retrofits are rolled out over time, as well as the impact that these retrofits would have. So this is some information on the analyses. All of the analyses I'll show have these factors in. So this is an analysis of 400,000 gas-heated houses in London at the building level. And these have matched EPC and energy meter data. We're focusing on building envelope improvements, so specifically glazing, wall insulation and loft insulation, and assuming that that's rolled out at roughly 15,000 per year between 2020 and 2050. And so what that means is that all the scenarios have the same starting condition as well as ending condition, but the only difference between any of the scenarios I'll show is the order in which those 400,000 houses are retrofitted. So the 2 scenarios that I'll show now, firstly are what I've called a sort of emissions reduction scenario, where houses are retrofitted in the order of the most predicted improvement first. So in the first year, the 15,000 houses with the largest predicted improvement will be retrofitted. In the second year, the next 15,000 and so on. And in the bottom row, the results, the order is instead controlled by cost effectiveness. So houses with the largest predicted improvement per pound of capital cost will be improved first. So what do the 2 scenarios show? Well, these 2 charts show how retrofits are rolled out across the different building categories across London. This pair shows the proportion of house types, and we can see that to maximize emissions reduction in the top left, rollout should start with detached houses in blue, followed by semi-detached end terrace and so on. And in contrast, the cost effectiveness scenario at the bottom, the distinction is less clear, with terraced housing starting much sooner. The right-hand pair, meanwhile, shows the rollout across building ages. So you can see in the top right that to maximize emissions reduction, rollout largely follows construction age, starting with the pre-1900 stock in red, with the post-1970s, 80s stock retrofits starting much later. In contrast, the cost effectiveness scenario at the bottom suggests that retrofits should actually start with 1940s and 70s stock, with the oldest pre-1900 stock in red starting much later on. And these trends partly reflect built form and the relationship between construction age and thermal envelope, but it's also strongly influenced by the types of retrofits necessary for the different building types. So in this graph, we can see how the retrofits are implemented over time. And we can see in the top left, the purple line, which shows solid wall insulation kick in very early on. And in contrast, the bottom left graph shows shows the solid wall insulation starting later, and instead the green line, which represents cavity wall insulation, starting immediately. And this change in prioritization is due to the massive difference in costs between these two retrofits. Finally, these two graphs illustrate the impact that these two approaches have on emissions and total costs. So the left-hand pair shows how emissions and energy use are reduced over the 400,000 houses over time, while the right-hand graph shows capital spend over the same period. And we can clearly see the impact of these two approaches. Now, the results I've been showing have all been for London as a whole, but we know, for instance, from the very first graph I showed that the distribution of EPC grades is not consistent across London, and the same is true of building types, ages, and so on. And this means that the different scenarios will affect different regions differently. So these three crude maps have been added just so that we can map the data within Excel, but they're effectively simplified representations of the 33 London boroughs. The first map, or the first pair, shows the proportion of houses within each borough that are retrofitted. The second pair shows the cost for retrofits, and the third pair in purple blue shows the impact on emissions. And these are effectively the overall values for each borough for a specific year. So now you can see in the bottom left that this is the year 2035. In this instance, the top scenario is the emissions reduction scenario, and the bottom uses the census aggregate information on multiple deprivation, and it instead prioritizes houses in areas of high deprivation first. So what I'll show now is some video which shows the rollout of retrofits across the London boroughs between 2020 and 2050 based on these two scenarios. And what you'll see, even if you don't quite catch all the details, is very clearly that the impact on the different boroughs is very different depending on the scenarios. So this has been a bit of a race through some of the work we've been doing with the 3D stock model. Hopefully you have an idea of what 3D stock is and what can be done with the model, perhaps with some interesting results. But it's worth saying this is very much an ongoing project, and there are a lot of areas of future work as well as projects that we just haven't been able to talk about because of the time. One of our big goals listed at the top is hopefully to expand 3D stock to cover England and Wales, and then all of Great Britain. But we're also looking for areas where it can be linked to more data, including the EPC input data, hopefully, and smart meter data. And we're looking to expand the analysis in a number of areas. There are also members of the team who are integrating 3D stock with highly detailed building simulation. Finally, I include some links here on the left. The first is a sort of video that gives a good overview of 3D stock. The second is a paper that goes into detail about about the project, as well as a lot of research that's been done with the model. Next, there are links to the LBSM and LSOM sites, which Steve mentioned. And lastly, just to say, although Steve and I have presented this today, the 3D stock is development from a much larger team who are listed here on the right. Thank you.